Firstly, let me congratulate you and the other scientists behind the Event Horizon Telescope. How is the physics world reacting to this image of the black hole?
I think the physics world is reacting very enthusiastically, I would say. Sometimes maybe a bit too enthusiastically, because there's many deep theories about space and time that especially come together around black holes that I think especially the theoretical physics world would like to understand. Things like string theory, information theory, emergence of space-time itself. And they have very high hopes of testing these ideas, on black holes. But I think the reality of what we're capable of measuring with real black holes is pretty far from the level of precision that they would need. So there's enthusiasm, but I think there's also sometimes a bit like overthinking of what we can actually tell them. On the other hand, I think sometimes people in the physics world don't realize how deep our modeling work actually goes, and they think that the beginning and the end of the project was just to take this, cute picture of a fluffy black hole. And of course, there's a lot more to it. So it's a bit of a conversation still.
There's one question that puzzles many of us. How did we take a picture of a black hole?
All right, well, there's a lot of things that could be said about that question. I think, the simple answer is if something emits light, you could take a picture of it, right? And you would think that, well, a black hole doesn't emit light, so how can you take a photo? And so the answer is we're not taking a photograph of the black hole itself, right? We're taking a picture of the light that is emitted by stuff that is just outside the event horizon. And then some of that light gets absorbed by the black hole, and then we don't see it, and that creates this shadow, basically, that's sort of imposed in the image. And then you have all these general relativistic effects. So the weird thing is that we're actually seeing some of the light that's produced behind the black hole, for instance, that gets projected into the front. So it's quite complicated. And what we're really looking at is a convolution of these space-time effects with messy astrophysical effects. And so, there's the challenges in interpreting that, because we have to pull apart these two effects. And then the challenges of how we actually, took this picture. And I think the simple answer for that is that, size is kind of everything. You're trying to look at something that's extremely small on the sky from our point of view. So these are supermassive black holes, but they're very far away. And so the size on the sky is on the order of tens of micro arc seconds, which means people use silly examples like reading, for me in Amsterdam, reading a newspaper in New York. That's about this precision you're trying to imagine seeing with a telescope, or seeing a donut on the moon. And that's requires basically a telescope that's effectively Earth-sized. Because the resolution of your telescope, how good you can see with the telescope, is basically a function of the wavelength divided by the size of the telescope. And so the bigger your telescope, then the smaller you're going to be able to see on the sky. So we can't use the Earth as a full telescope, or, that's difficult. So we make an array of, well, we didn't make it. We actually are borrowing telescopes that exist across the Earth, binding them together, and getting them to communicate with each other. And that is very technically challenging. So, over the years, this had to be prototyped, and actually changing the way the protocols that all these different facilities could talk to each other with similar electronics and rates. And then also, you really need to combine the data to be able to find the positive interference, basically, between all of these different facilities. And you can't do that in real time. So what you do is you locally kind of time tag literally every wavelength of light using atomic clocks, have to record this, and then everything gets packed up, and you're talking about petabytes of data. So it can't be sent over the internet, and you have to put it in literally physical boxes of big chunky disks that weigh tons, and send this off via planes to supercomputers that can then correlate this and use this, effectively matching the delay to figure out what the delay in light travel time should have been from the object you're looking at the sky, keeping track of the baselines. And so that calibration is extremely difficult as well. And then there's a lot of, other data systematics and calibration that have to be accounted for. So I think when you look at the fact that this had never been done at this wavelength and at this scale before, It's not surprising that it took several years to get the first papers out. So lots of challenges. I'm probably forgetting some, but those are the main ones.
How does this picture of the M87 black hole help us understand the magnetic field structure around a black hole?
Yeah, so I mean, actually, the type of light that we're observing is what's called synchrotron emissions. So this is light that people might be familiar with, also from other types of facilities. Synchrotrons are named after that, but you basically get this when you have relativistically moving charged particles in a magnetic field. So by definition, the fact that we're seeing synchrotron light tells us that the plasma that's emitting it is highly magnetized. But then, can we actually constrain exactly the configuration of these magnetic fields and the orientation, the strength? So one of the things that radio telescopes, which includes the Event Horizon Telescope, can do is actually measure directly the polarization, the EVPA, or the electric vector polarization angle. And that angle is perpendicular to the direction of the magnetic field line. So you can literally see a projection on the sky of and trace out the magnetic field lines. The tricky bit is that this is still all being convolved by gravitational effects, because we're looking at light that's coming from within the gravitational, really strong bending regime, near the black hole. And so we have to use our models also to interpret what we're seeing. But then from that, this is assuming this is a black hole, and assuming that general relativity is true, which is when we do this type of modeling, our baseline assumption. Now, of course, we think of other types of models, but I mean, when we're trying to interpret the astrophysics, we stick, to things we think we understand. Then there are basically, we know that if we have very strong vertical magnetic fields kind of coming out of this sort of disk of material that's infalling into the black hole, the way it will look from our point of view will be a bit twisted on the sky. We actually use the similar definitions of the twistiness that's been used, for instance, in the cosmic microwave background to look for different kinds of E and B modes, if people are familiar with that. So we use the same kind of twistiness factor. And what we found was that the magnetic fields really close to the black hole and M87 galaxy are extremely strongly, dynamically strong, and highly what we call poloidal, or kind of ordered and coming out vertically. And that's exactly what our models would predict you need to launch strong jets. So, that wasn't in effect so surprising. I think the thing that was more surprising is that we've looked at two black holes, by now. So there's M87, but also the one in our galactic center, Sagittarius star. That one, we see quite similar magnetic fields, very strong, very ordered. We don't see strong jets. And that is kind of against our theory, or something's weird. Either the jets are there and we're not seeing them, which is also possible because they'd be very weak and hard to see in this very complicated galactic center, or our models are wrong. So either way, it's kind of interesting, but that's where a lot of the attention is going right now.
When one looks at the image of the M87 black hole, it's not hard to notice that there is a glowing ring around the black hole. What is this glowing ring?
So I think the important thing to remember is that some people say, oh, you're looking directly at, a disk of material. And the ring shape is because of the gravitational effects, but it's affected as well by the emission of the light. And I think there's a few things you have to unpack in this question. One is the source of the light. So we wouldn't see anything if there wasn't basically extremely hot relativistic plasma. So we've got something we don't know the entire composition of, but like most things in the universe, is probably mostly ionized hydrogen with some traces of other things. And then you have strong magnetic fields that gives the synchrotron light that we see. And then, of course, it's being bent and warped by space-time. And you can have photons that will come very close to the black hole and actually go around once, twice, even, billions of times in principle. I mean, they just go around, and then eventually we only see them if they escape. So somewhere in that image is something we call a photon ring, which is basically the sort of orbits of photons that get very close to the event horizon but don't actually fall in, and they trace the shape of space-time. And so all of that is being convolved into a very sparsely sampled phase space, which is why the image is quite blurry due to the fact that our telescope just isn't, super super high precision, because we had to fill in the Earth with just a few telescopes.
A cursory image search of a black hole often depicts jets propelling out of the black hole. What are these jets?
Yeah, so these are questions that we're pretty busy trying to understand. The jets are just a physical fact. We see many black holes have these enormous jets of magnetized plasma. They can extend out to billions of times bigger than the event horizon size, and that means they really go beyond the galaxy, even into larger groupings of galaxies, and can infect and talk to the environment. So, we think that they play a really important role in helping regulate things like galaxy evolution and so on. And we know that they have to be created, just the energy has to be coming from the most energetic part of the system, which is the black hole itself, just because if you think about the potential energy, where mass energy being falling near the black hole gets its basically gravitational potential energy converted into other forms, you need this deepest part of the potential well. So everything is rooted within, something like tens of times the size of the event horizon, maybe at most, 100 times, but really concentrated to the center. And we know that this is not unique to black holes. So there are many other astrophysical objects that have jets. So it seems like as long as you have some kind of gravitationally bound infalling material, and as long as there's magnetic fields in that material, and as long as there's some kind of rotation axis, you get outflows. So this seems to be a kind of universal feature that we think has something to do with the buildup of magnetic fields. It actually helps allow angular momentum transport via things like viscosity and turbulence, and allows matter to both go outwards and then allowing matter to go inwards. And then somehow when the fields get strong enough, you're managing to actually, the fields in the plasma are basically frozen in together in many cases. This is ideal. What we call ideal magnetohydrodynamics. So where the fields are, the plasma is, and the plasma can also get pulled out by centrifugal forces, and then the magnetic fields get pulled out as well. When you have a black hole, you get an extra boost where the magnetic field lines can actually press onto the working surface of the black hole, which is called the ergosphere. So it's actually outside of the outside of the event horizon for a spinning black hole, and you can spin up the magnetic field lines, and this basically creates magnetosonic, waves that can pull energy also in principle out of the rotation of the black hole. So the power being tapped by these jets is coming ultimately from gravity, but then it gets translated through a lot of plasma physical processes into magnetic energy, into particle energy. One of the big problems is we don't know the content other than the magnetic fields, and we know there has to be most of the synchrotron light comes from leptons, so electrons and positrons. We don't know how many positrons there are compared to electrons. We also don't know if there's protons, ions. We assume that they're there, but they're harder to see because if they get also accelerated, we will generally see the secondary products of their collisions, like neutrinos we can see on Earth. We can see these accelerated particles directly on Earth, but we don't know where they came from because they're hard to be directionalized. So we think that these jets are the source of these, but it makes a big difference for us for the theory, because if you think about trying to push some kind of plasma up to nearly light speed, whether it's made up of mostly light particles like leptons or heavy particles, is a pretty big factor in your power, and also the punch that these things will have when they impact on the environment. So, as far as the broad brush strokes, we know kind of roughly how these things are created, and we can reproduce them in our computer simulations. But having the full picture with all the details, and especially the physics of particle acceleration and which particles, that's where we're really, kind of doing a lot of investigations at the moment.
What are the different astrophysical objects that you use to study these jets? And are these jets different for different astrophysical objects?
Yeah, so we see like I said before, anything that has these kind of properties of some kind of gravitationally bound infalling material, magnetic fields, you often get these jets. So, for instance, we see jets coming from the formation of young stars. There's condensing gas in systems that eventually become planetary systems with a star in the middle, but it seems like they're often used as an exhaust from the system to get rid of maybe excess angular momentum to allow things to fall in. Young star objects have jets. We also see jets coming from other types of compact objects, whether it's white dwarfs or neutron stars, as long as they're accreting. And of course, recently there was the first electromagnetic counterpart of emerging neutron stars that were eventually created gravitational waves, but there was this kilonova, and then later there was a jet coming out of this. So there's a lot of places where we see jets, and we see jets in black holes from supermassive down to stellar mass black holes. Where they may differ is really in like their power and perhaps in their content. And as I was also saying, the power rooted ultimately comes from the gravitational potential well. So the key there, right, is that the gravitational potential goes as the gravitational constant times m over r, right? So you really need this ratio we call the compactness. The mass to radius ratio is the key factor. And so black holes are the most compact objects of all the compact objects, and that's why you expect them to have the most, power. Their escape velocity is going to be the highest. What's very puzzling is that there are a couple neutron star systems that seem to have jets that are equally powerful as their counterpart stellar mass black holes. So these are basically black holes and neutron stars that are in a binary system. They're eating their normal companion star, and then the black hole starts to do things like emit jets similar to the supermassive. That's something that's a really big cause of debate, because every ounce of logic in theory would tell us that the black hole has something special, that it should be giving more power, that we should be tapping the energy of the black hole. So if it's true that these neutron stars are launching jets that are equally powerful, we're missing something. But it could also be that we're not correctly interpreting the power in these systems. So there's also observational effects. So this is a very active part of area of debate in the field at the moment.
How well do the existing theoretical models correlate with the multi-wavelength data of these jets? Are the models consistent with the data?
Well, I think the honest answer is that the more simple the model, the better it fits, right? Because what you do is, if you don't really understand what you're doing, you parameterize your ignorance into some parameters, and you just turn the knobs, and the more knobs you have, the more free parameters, you basically get better fits. So what I would say is that at the moment, most of the models that we have, the broad stroke ideas, and we can simplify the models quite a bit, and we can get pretty good fits. And I would call that reactive modeling, which means, you throw a data set and we can say, okay, here we understand the basics and we can tune these knobs and we can fit it. The problem is that by having so much ignorance in these models, we create degeneracies in interpretation. We don't know exactly which one is correct. We can't make predictions, right? Because we need a first principle approach. So the Event Horizon Telescope project is actually very important for this, because besides the image itself, which is just one thing we do, we actually also take simultaneous data from other facilities on the space and ground at the same time that we're making the image, really going from radio to TeV gamma rays, which is like 20 orders of magnitude in frequency. And the reason this is important is because these systems, if you think about it, you're going from particle scale. Near the black hole, you have little particles moving around that are generating these magnetic fields and being influenced by the magnetic fields and accelerating and radiating. So the light is telling you what's going on at these microphysical scales. But then the same magnetic fields are launching, these macroscopic things that go out to billions of times. So the scale separation is something like 15, 20 orders of magnitude. We just don't have the capabilities of any one first principles, computer simulation to handle all of this. So we break the problem into different parts. And by actually developing models where we try to fit all of the constraints. So, if you take one particular simulation of a black hole where we run, we throw stuff onto a black hole in a box with, a Kerr metric and a black hole in it, and we see what happens, and we launch jets. And then we, make the light to make, with general relativistic ray tracing, and we can reproduce the image. That's one model. But that same model will have locked in conditions about the magnetic fields near the black hole and the gas properties. And that will also determine, because of force balance and all of this, the properties of the jet that's launched and the opening angle of that jet and the dynamical motions in that jet. Those are things we can measure as well with other facilities. And we do for the sources, that especially for M87, which is our primary jetted black hole that we look at. And then we also have this 20 orders of magnitude of data that can be coming from all these different parts, both near the black hole, but also far out in the jets. So if we can get one consistent model that puts that all together, I think we would be really turning things around and actually having much more of an ability to really test, the plasma physics models, to test the interactions of magnetohydrodynamical plasma in space-time. We're in the baby steps of that right now. I mean, that's where we are working, many of us in the EHT collaboration. We're working as a collaboration, but also in our own groups. That's what my group does. We're trying to build these kinds of models that can do that. And so far, we're very far from being able to fit things at a first principles level. So that's where the exciting stuff comes.
Looking at the bigger picture, how do scientists use these images of the black holes to understand the evolution of galaxies?
Well, I think, because we only have 2 black hole images now, right? Whereas we have millions of black holes we know of, it's a limited picture, but it gives us a kind of unprecedented picture of one very important piece of the problem, which is, the source term. And what's important to realize is that black holes seem to grow together with their galaxies. And what seems to happen is that when galaxies are growing, also the black hole manages to accrete more material, to gather more material, which is how it grows. But during those phases, it also goes through an active cycle, which is often when it starts to launch these jets or have these big winds. And those jets and winds will then impact the outer galaxy and can actually cut off their feeding source. So you get in this kind of like cycle or feedback loop. And so if we can understand what sort of kicks off these activity cycles, and then we can try to understand, what makes a black hole active versus not active and what kind of drives this. So what's interesting is that we only have these 2 black hole images, but actually we have many more. I should point out that 2017 was just our first year, and we're actually taking data almost every year. So we have many more images of the same 2 black holes, but also we have other black holes we look at where we can't see the black hole itself, but we can see very close down and we can see these jets. So we have a kind of a population. But at least for Sagittarius and A star and M87, they really represent 2 different extremes of these cycles, where Sagittarius star is in this dormant quiescent state that probably most black holes in the universe are in, where they really aren't doing much of anything. And that's how they sort of rest in between these cycles. So right now, our black hole in the galactic center is not growing. It's just doing very little. It's getting very little material. But M87 is actually also not growing very fast right now. It's getting quite a bit of material, enough to power these jets, but it's still relatively low level. However, if we can understand the bridge between these different activity cycles from quiescence up to this moderately active M87, and then start to connect it to some of the other black holes that we do see with EHT, where we don't maybe see the black hole itself, but we see very close down to tens or hundreds of event horizons, those can be extremely bright up to these maximally, emitting black holes. We can start to develop a better picture of this whole process. So I think, if you look at cosmology, especially the more computational cosmology, where they try to understand the largest scales of structures today and how they developed from the seeds that were set, right after the Big Bang, everybody basically agrees by now that something has to happen at the largest scales to truncate the size of the massive galaxies. Like if you don't include some extra process, you get too many massive galaxies in these simulations. So the only thing that's really out there that's big enough are the jets from black holes. So, but we don't know how the details work. And this is going to help us tell the cosmologists, what to put into their simulations ultimately. Interestingly, one of the things that we can do is we can look at black holes that are active in what are called clusters of galaxies. So basically most black holes, most galaxies grow together in these big groupings, like these nurseries of galaxies, and they're the largest bound structures in the universe. And they're full of hot X-ray emitting gas that's basically heated by all the combined actions and mergers and black hole activity and whatnot. And because we can measure the temperature and the gas density via, it's basically Bremsstrahlung from the X-rays, that gives us a handle on calculating how much energy is being dumped by an active black hole, because they will blow little bubbles in this gas, and that the bubbles are overpressured, they're buoyant, and they start to move away from the black hole. And we see pairs of these, we see these pairs of bubbles, and we can use just PDV work more or less, to figure out how much energy. So per activity cycle for a nice size, active black hole, an activity cycle can last somewhere on the order of 10 to the 7 years, and will dump the equivalent of hundreds of billions of supernova into the surroundings. Then it'll turn off again for something like maybe 10, 50, 100 million years, and then it starts again. So we can measure this all from looking at these buoyant bubbles in distant systems.
What is the future direction of your work, and what are some questions that you would like to tackle?
I guess I would like to get to the point where I could actually predict what's going to come out of a black hole as a function of what goes in. I mean, this fact that we're not predictive is very frustrating, and it's at the heart of many problems, in the field, whether we're interested in trying to understand particle acceleration in jets and the source of ultra-high energy cosmic rays, or cosmology and feedback. And, there's a lot we don't understand. But to get there, we have to get to this point of understanding this scale separation between what's happening at the plasma physics particle scales and then these larger scales. And I think that's where my focus is really going. Like in my group, we're looking both more some of these simplified models to understand some of the trends in the data, but then also really doing the detailed models where we go and we talk to our plasma physicist friends, and we say, okay, well, we have some kind of background magnetic field and maybe some kind of composition of particles. Can you run this in your kinetic, something like a particle and cell simulation, and tell us more or less what kind of particle distributions we might expect to get out? And usually what happens is this is parameterized, and then we can put this back into, it's like a subgrid, what we call subgrid model. We can put back into these larger scale simulations and create light that's informed by plasma physics, and then we can test it against the data. And that's where I said we're pretty far from ground truth at the moment. So in the next years, I'm going to be working quite closely with people both from the plasma physics point of view, and then also getting all this multi-wavelength data and trying to put all of this together and seeing if we can maybe even discern which scenario is the most promising for exciting the particles, because there's quite a few choices. And then if you can figure that out, you can figure out a bit about where this process might be happening. And to give you just an example, in our very high resolution simulations near the black hole, we're starting to be able to resolve things very similar to the solar surface. So we see vortices and current sheets, and we see instabilities that break into little plasmoids. And these are all regions where you can have reconnection. So magnetic reconnection in the magnetosphere of the black hole is one candidate for where you start to light up some of the emission that we might be seeing. But then on the other hand, you can also get you have two stream instabilities, because you can have different layers of plasma rubbing against each other, and you can get shear acceleration, turbulence acceleration. I mean, there's a lot of things that that we don't really know which one is the dominant one, and it can all be happening in this very complicated stratified region. So trying to figure out what is the culprit. And then, it is probably not going to be just one. We're starting to suspect that maybe really close to the black hole, you're getting unavoidably some reconnection current sheets. And then further out along the jets, you're probably getting unavoidably some turbulence and, some kinds of instabilities and shear acceleration, where you get different things. And trying to figure out which one dominates in which part of the system is going to be, I think, the way we'll have to put this together.
Thank you very much for this amazing session. Lastly, what piece of advice would you give to our young audience?
Well, I guess I would just say, always stay true to yourself, because you're only going to live once, at least as far as science is concerned. Don't buy into what other people think. And I think part of the problem is with, social media, everybody's paying a little bit too much attention to what everybody thinks and looks like and whatever. And I think at the end, if you don't figure out what makes you happy, you won't be happy, right? It's not going to be the same answer as for everybody else. So whether it's what you want to pursue scientifically or how you want to do it, there's just not one way to be a scientist. There's not one way to be a good person. So that's my sage advice.